Okay, this is the Math 2460 Zoom meeting, November 17th. We have a participant. Would you like to tell me who you are?
Madison Brown.
Very good. Appreciate you joining us, Ms. Brown, this morning. Let me go through the assignments and we'll ask if you got any questions. No quiz this week. We got sections 10, 2, 3, and 4 to finish the class. Test 5 on Friday over these. It's easy enough. There's no review sheet. Covering this in the same format. So 10-2 practice problems are here. 10-3, a little longer here, and 4, a little longer. And then on WebAssign from 10-2, problems 1, 2, 3, and 4. 10-3, just 3 and 4, and 10-4, 1, 2, 3, and 4, and email me the percent of these 10 problems that you get correct. Did you have any questions this morning?
No, I just wanted to dive right into 10.2 and 10.3.
Okay. Sure thing. 10.2 is a little strange. It's got no calculus in it whatsoever. And then we bring in some calculus in 10.3 and 10.4. But yeah, we'll charge in. I've mailed out, you're the first participant I've had this week. I've mailed out final exam review sheets and everything. Is everything clear about the rest of the semester or the end of the semester?
Yeah, so we just have this week and we do the tests over section 10. And then on Tuesday next week, we have the final review that we're going to go over.
Yeah.
And then next week after Thanksgiving, we take the final.
That's correct.
Okay, and then that's just it?
That's it.
Okay, yeah, I'm good with all that.
Okay, the final exam will have problems. It's comprehensive. It'll have problems, from the beginning to the end of the class. It'll be the exact same format, true or false, on answers on a Google form, and it's worth 10% of the grade.
Sounds good.
Okay. They've really mashed the end of the semester here real compact by ending like this. Ordinarily, we'd go to at least like December 10th or something, and really into December, pretty good, but not this semester. Okay, charge into 10-2. They call it plane curves and parametric equations. All right, basically in a nutshell, it's a way to graph and work with non-functions by writing them as functions. Let me give you, hopefully, instead of charging into the gibberish in the homework and everything, let me try to give you an example that you're hopefully familiar with. If I had you show me a graph of x squared plus y squared equals 1, would you know that that is a circle? The center is at 0, 0, and the radius is 1. Is this pretty familiar to you?
Yeah.
Okay. Let's say I wanted you to find the slope at, say, x equals, well, at that angle, I'm trying to think angle pi over 4, 45-degree angle. And basically, it's the unit circle, and the x would be root 2 over 2. Well, the only way you would presumably know how to do it is you'd have to solve for y. Well, y squared is 1 minus x squared. Y is plus or minus square root of 1 minus x squared. And the plus root is the top one, plus square root 1 minus x squared, and this bottom is negative. And this is how you could graph this on the calculator by individually graphing these, and the calculator would treat them as functions and overlay this, creating the full circle on the calculator. So if I want to find slope, which is dy dx, I take basically dy dx, which is d dx of the top curve. See, I'm on the top curve of square root 1 minus x squared. And I'd have 1/2 1 minus x squared to the negative 1/2. See, that's 1/2. Square root's 1/2 power, comes down, copy it down, subtract 1. Look inside, chain rule is a negative 2x. Is this going too fast?
Not for me.
Okay. So you see the 2's cancel, you can send this down, and you wind up with a negative x over square root 1 minus x squared. So you have a formula just in terms of x for the slope. So now if I want to plug in x equals root 2 over 2, because remember at 45 degrees, your coordinates are root 2 over 2 and root 2 over 2. If you remember your trig. So my slope, dy dx, then would be negative root 2 over 2 over 1 minus square root of 1 minus root 2 over 2 quantity squared. And I would wind up with negative root 2 over 2. Hope you're having fun. We're going to get to the point of this section here in just a minute. I'm just trying to show you the old way. Maybe you'll appreciate the new way. If I can finish this out really quick, square root of 1 minus, now when I square this, I'm going to get 2 over 4. Well, that's 1/2. 1 minus 1/2 is 1/2. So I'm going to get root 2, negative root 2 over 2 over square root of basically 1/2. Well, if you remember your thing, because I'm going to get 1 minus 1/2 is 1/2. So I'm going to get negative root, trying to finish this on one page, over 1 over root 2. Can you tell I'm going to get negative root 2 over 2 times root 2 over 1. So this flips around. Can you tell I'm going to get negative 1? Speed this up slightly. Are we going too fast?
Nope, I got that.
Okay, I don't know if you remember that makes sense to you. Your 45-degree line, y equals x, would have slope 1. If I do a tangent line to this circle, it's perpendicular to that. And if you remember, you flip and change signs. So this is all the gibberish you have to go through on the old way to show this. Well, somebody who knows who came along and said, you know, I hate all this crap. I want to do it differently. So they invented this process called parameterizing, or say they parameterized the curve. X squared plus y squared equals 1. I'll redraw it. And that means they set x equals cosine of t and y equals sine of t, and they call t is a parameter. If I make a little table of t and then my x coordinate being cosine and my y coordinate being sine, I'll just do the first quadrant. Can you see you're going to get the same curve? Start with t is 0. Cosine 0, your x coordinate will be 1. Sine 0 is 0, which gives you this. If you go up to pi over 6, I'll just do circle numbers. Your x is cosine of pi over 6. That's root 3 over 2. I believe that's 0.866. And sine is 1/2. Sine of pi over 6 is 1/2. You're up to this one. Pi over 6, pi over 4. At pi over 4, cosine pi over 4, you're going to get root 2 over 2, which is 0.707. Same with sine. Pi over 3, it reverses. You'll get your 1/2 on your cosine, 0.5. You get your root 3 over 2. Are we going too fast? Finally, pi over 2, cosine pi over 2 is 0, and sine pi over 2 is 1, and you wind up here. That's just the first quadrant. You can keep going around and draw the whole circle. Is that too fast? Should we slow down and let you absorb that more? Or are you so awestruck no one can speak?
I think we're good to keep going.
Okay. So in other words, you start with a non-function. You remember how we know it's a non-function? It doesn't pass a vertical line test. But you bust it up into two pieces, an x-coordinate and a y-coordinate, that are functions. And 10.2 is only about graphing parameterized curves. They're going to give you random parameterized curves. Right now, I can't finish this up and show you how you get that same slope. I can't do that till we do 10.3, which we'll do today. Maybe it's going to be tough to get through all 3 sections today. It's a lot of stuff, even though none of it's really very hard. But when we hit 10.3, I'm going to come back to this and show you where we get that slope. But let's right now just talk about, just do some homework and show you how easy this is, just parameterizing these curves. If you look at the homework, 10.2, 707, I guess we'll start with the first one. I think I just asked for 5 to 21. Yeah, there's no point in doing all of this. It's nothing but graphing and some algebra. So I just asked for this first little section of it. That should give you the idea. All right, what they want, sketch the curve represented by the parametric equations and eliminate the parameter. That's where the algebra comes in. We'll show you that here. So 5, they want you to sketch the curve. And they're telling me that x is 2t subtract 3 and y equals 3t add 1. Again, this is just a random curve. Now we're into just random math problems doing the idea. Okay, we're going to use the TI 84 in parametric mode. So if you go to mode, 4th line down, you're used to, if I get the glare off, okay. You used to be in a function mode. That's where you do y versus x, your normal graphing y function of x. All right, 10.2 here, PAR stands for parametric. So we're going to come down over to parametric. Hit enter. And now when you go to graph and y equals, look at the change that's going to be made. You now get pairs of functions, x coordinate and a y coordinate. So now we're going to enter our 2t minus 3, 2. Now I get the t straight off the x, this like you're used to getting it. We're used to getting x. But I hit it, I get a t and subtract 3. Now I enter the y and it's 3t and add 1. Okay, we need to pause for station identifications. Any questions about this? Everybody's so awestruck. All right, I'll assume I can go on. Notice what happens when I go to window. You're used to just an X min, X max, X scale. Well, you get that down here. But at the front in parametric mode, they're letting you set the values for T, just like I did here. The calculator is doing this exact same thing. The calculator is plugging in values for T, and you can set this. This is a T min, T max, and you can set what its increment should be. All right, they don't tell you what to use. That's where things get confused. They don't tell you what to use. I typically use a standard like 0 to 10 by 1 to start with. And then if I check the answer in the back and it looks completely different, then I try to, mess around with it. All right, your X min, X max, try to keep that the same, negative 10, 10. This is what's actually shown on the screen like you're used to, negative 10, 10, and 1. So the only new thing is that you set this T min, T max is plugging into these X and Y coordinates for T, generating X and Y coordinates to generate your curve. Hit graph, and I'm pretty much getting a straight line, crosses the Y axis at 1, 2, 3, 4, maybe midway between 5 and 6 up. 4, 5, 6, somewhere like this. And let's check this to see if that's pretty close to what they get. This is 10-2, number 5. Otherwise, we may have to adjust the windows. Yeah, that's pretty much what they get. We're not really, the arrow on it is supposed to be the orientation. It's between 0 and 10, it's drawing points this direction. I don't really pay any attention to that or ask y'all anything about that. I consider that a pretty minor point. Does anybody want any more examples of doing that? Oh, we have not shown you the eliminate the parameter. Yes, the second part of the directions. Write the rectangular equation by eliminating the parameter. Okay, sounds like complicated gibberish. Trust me, it's the easiest thing in the world once you see it done, just algebra. When it says eliminate the parameter, it means find your standard y equals f of x. Y in terms of x, and the t is gone. All right. Some of these you can, if you see it, you can do shorter than this, but here's the standard procedure. It's really 2 steps. Number 1, start with your x equation. Solve it for t. So on this one, my x equals 2t subtract 3. That means x plus 3 will equal 2t. And that means divide by 2, x plus 3, divide by 2 equals t. And then the second step is plug into the y equation. So if y equals 3t add 1, this is t. So y equals 3 times x plus 3 divided by 2, add 1. And then you can simplify it out. That gives you 3x plus 9 all over 2, add 1. You can see 3 halves x, so y is 3 halves x. And if you want to figure out you have 9 halves plus 2, you have 11 halves. 1 is 2 halves. 9 halves plus 2 halves is your 11.5. And you see you get a straight line, mx plus b, with m at 3 halves and a y-intercept. Sure enough, halfway between 5 and 6, 5.5. You graph this graph in function mode, function mode, I think the calculator used FENC, function mode. You get the identical graph. It's identical to this in parametric mode. Hope you all believe that. Do we need to show you any more of those just to try to drive it home?
Sure, why not?
Which one you want to see? They get to E by mostly algebra down through 15, and 17 that has an E. 19 and 21 have trigs.
Let's do 1E and then 1 trig.
All right, you want to see 17?
Yeah, let's do that.
Okay. Pretty much plug and chug into the calculator. Page 707, 17. These are the parameters. X is e to the t. Y equals e to the 3t, add 1. So if I want a graph, that's what I enter. Clear. So x was e to the t. Y is E3T, add 1. I'll keep the same window, 0, 10, 1, and negative 10, 10, 1. Just see what happens just as a start. And if I have to adjust it, then I will. Graph, and I'm getting pretty much starting, spontaneously generating, and kind of rising up. I usually do check the graphs at the back just in case. On the test, do you want me to tell you what to use for the t-values? Or would that be too nice of me? You'd think I'm a nice guy. You want me to, in other words, do you want me to tell you what window to use on the test?
Oh, yes, please. Oh, yeah.
Oh my goodness, please, so polite. Okay. Well, you promise not to think of me as a nice guy. Remember, I'm an evil math teacher. I'm not a nice guy. Okay, yeah, it's pretty close. If you look at 17, could extend the t back a little bit, show more of that hook into the y-axis. But it's pretty close. All right, so we're going to eliminate the parameter. Basically eliminate t. So yeah, basically you want to start with your x equation because you want y equals f of x, y in terms of x. So you start with the x equation, solve for t, which means you're going to need a log on both sides. Undo the e. So t is equal to log x. And then second step, sub in 4t into y. So y equals e to the 3, and then t is log x, add 1. So I'm putting log x in for that t. And you see how I got just nothing but y's and x's. Now, this is perfectly legal, but the book is going to simplify it. Remember, you can put that up. So that's a y equals e to the log x cubed, add 1. Then these undo, and y is x cubed, add 1. And there is your equation in function mode. It's basically a cubic curve shifted up 1. Questions about that?
No, sir.
You still want to see one more?
Yeah, can we do a trig?
Okay, have a preference?
I do not.
I'll try 19.
Sounds good.
Okay. X equals 8 cosine theta. Y equals 8 sine theta. All right, now notice they're using a theta symbol for angle, but don't let that bother you. You're still going to put in 8. Oh, you want to be in radian mode as well, which I am. You got to be in radian mode, and so you're going to want to enter 8 cosine t and 8 sine t. Pretty straightforward. Once you get the hang of it, it's pretty straightforward, plug and chug. And I guess we'll use the same window, graph. Okay. I don't know if you, I did a cosine example, a sine example, and that was a unit circle with no coefficients. This is going to be a circle, radius equals 8. Now I'm kind of, it's overwriting itself, so probably a better window on the t is probably 0.2 pi. Yeah. Now I know that doesn't look like a circle, and that's because the resolution, let's say, is pretty crude. Every t value, and I'm not quite getting it to close. So if you really want to tighten it up, you can say go pi divided by, I don't know, 24. Oh, okay. And now it looks more like an ellipse than a circle, but that's because there's not the same number of pixels horizontally as vertically. But we're zeroing in on it. Questions about that?
No, sir.
Okay. All right, so this is going to be, you can follow that same procedure that I just showed you. And if you want to be really anal, do exactly the same way you can. But if you recognize a circle, the book will use, here's the trick, we use sine squared plus cosine squared equals 1. Well, can you see here a sine theta is y over 8? Cosine theta is x over 8. So I'm getting y over 8 squared plus x over 8 squared equals 1. All right, so 8 squared is 65. Multiply through by 64. I'll get y squared plus x squared equals 64, because your 8 squared, you're going to cancel the 64s here, then use 64, or x squared plus y squared equals 64, which is your circle centered at the origin with radius 8. And I believe that's the form they're going to have, 10 to numbers 19. There you are. X squared plus y squared equals 64. Now, I can do it the other way if you want me to. Anybody want me to do it had to do it the other way because there's no identities, for those, for 5 and 17 and et cetera. This is just using trig identity. When they use trig, they like to use trig identities. Anybody want to see it done the other way? Solve for theta here in the x equation, plug in here. I would be thrilled to show you it all works out. We're so awestruck, no one can speak.
Why not? Let's do it.
You want to see it done?
Sure.
All right. So step 1, you'd start with that cosine theta then is x over 8. So your theta is arcsine of x over 8. Arc cosine, my fault. Arc cosine of x over 8. All right, well, sub in the y. So that gives you y equals 8 sine of arc cosine of x over 8. So the rest of this is to work this out, and we got to get back to this. So on your triangle, your cosine is going to be adjacent over hypotenuse. Can you tell that this leg is going to be 64 minus x squared? This is going too fast. This is adjacent over hypotenuse. And then you'd go this squared, 64, minus this leg squared to get the square root, we get this leg. Are we going too fast?
We're good.
Okay, so this is giving you the sign on this then is opposite over hypotenuse, square root of 64 minus x squared over 8. So you're getting 8 square root of 64 minus x squared divided by 8. Well, your 8's are going to cancel, so y equals big square root of 64 minus x squared. Square both sides, then add the x squared over. Voila, x squared plus y squared equals 64. So in effect, this is just a trick to avoid a lot of this gibberish. But the gibberish works. Just happens to be a lot longer and unnecessary when you can use a trig identity. Did this prove anything to anybody or only to me? We're so awestruck.
Yeah, I did. Thank you.
All right, well, that's basically all of 10.2. There's not a lick of calculus in it whatsoever. No derivatives, no antiderivative, nothing. Just straight graphing in parametric mode and a lot of algebra gibberish to eliminate parameters. 30 minutes, and should I get to 10.2? I'm sorry, 10.3.
Yeah, let's do it.
We're ready for 10.3. All right, this is where the calculus comes in parametric mode. 10.3, calculus in parametric mode. Okay, the basic equation page 710. In this box right here. I've got an x equation, and we'll call it an f of t. These switch it up, make it a g of t. My dy dx is dy dt divided by dx dt. Y'all understand how simple this is? It just means I need to take the y derivative on y and divide it by the x derivative, and I'll have my dy dx. Do you see why? If I go dy dt times dt dx. So you work this out by flipping the bottom, your dt's cancel and you're left with dy dx. This is Leibniz's contribution or Leibniz's genius in Leibniz notation that you could show this. Let me go back to that first circle, because now we can show on the unit circle pi over 4 that the slope was 1. Negative 1, I'm sorry, slope was negative 1. Okay, without doing all that gibberish and finding the algebra forms for these things, remember we had x was cosine t, y was sine t. My dy dx is then dy dt over dx dt. Well, dy dt, that's, I'll write it out also, that's d dt of sine t. Bottom you have d dt cosine t. Well, your derivative of sine is a cosine. Derivative of cosine is a negative sine. You could write it as a cotangent, but I'm not gonna. because I wanted to plug in, my pi over 4 is my angle. So I had plug in pi over 4. So I get a cosine pi over 4, negative sine pi over 4. Can you tell I'm going to get root 2 over 2, negative root 2 over 2. These are identical. You get your negative 1. If I go back to the page where I had it. So you can see, here's where I worked out the gibberish the old way. You had to get your algebra forms for y, go through your derivative rules. You wind up plugging in the x coordinate, root 2 over 2, and you eventually get to negative 1. Here, using parameters, I just do a simple y derivative, simple x derivative, they divide. I plug in the parameter value, which is the angle pi over 4, and sure enough, I get the same answer. By the way, we should have a caveat. Your dx dt cannot equal 0, of course. You'd be dividing by 0. I don't hear any oohs and ahs. Are we so awestruck we can't speak?
Yeah.
Basically, then you're going to have problems using this. They do go on and do a second derivative, page 711. A second derivative in parametric mode works out, turns out d dx of dy dx. And you wind up taking d dt dy dx of your first derivative and all dividing by dx dt. And again, I could unravel this by flipping stuff around and show you. I don't know if you really care, but that's where I'll do a third derivative as well, but I'm not going to write that down. So there's where they get their second derivative. You wind up dividing them all by dx dt. You wind up figuring your dy dx, take another derivative on it with respect to t, but dividing by dx dt. Are we ready for some homework for this?
Yeah, let's do it.
Okay. Page 715. Okay, this was you're 10.3 now. That's page 711 showed this formula. Page 715, first homework problem 5. Your x is t squared. Your y is 7 minus 6t. Find dy dx. Well, after you do a bunch of these, you wind up just charging into it. But just to show you again the steps, you're going dy dt divided by dx dt. Can you kind of do these derivatives in your head? The dy dt will be negative 6. The dx dt will be 2t. And you wind up with negative 3 divided by t. And that's really all they want. Is this too fast?
No, it's good.
Okay. Yeah, that's all they asked for. Now, I'll warn you, I'm going to shorten up the next section. You go down to number 9. It says dy dx and dy and second derivative, okay, at the values of these t. So they're going to want you to plug in a t value into both of those. And then it says it wants concavity. Forget concavity. That's Calc 1. I don't want to, it gets too deep into it. I don't want to get into concavity. We will not mess with concavity. I'll write that out. Don't mess with concavity. You want to see one of those? They give you some algebra ones. 13's a trig, 15's a trig, 17's a trig. You have a preference?
Let's do a trig one.
All right, we got choice 13, 15, or 17. You have a preference?
Let's do 15.
All right, 15. Seven 15. 2 plus secant theta. Y equals 1 plus 2 tangent theta. All right, we're going to first find dy dx. Sorry. And the parameter is, sorry. It's generic. Well, it is actually dy dx. Yeah, it is actually dy dx, but we're going to be at theta in 15, negative pi over 3. And then secondly, they want d squared y dx squared. And again, at theta equal negative pi over 3. Okay, that was given right here. So they want you to find the formula for these two and then pop in whatever value they give you. This one's negative pi over 3. Can we just plug and chug?
That sounds good.
So you need the y derivative. So ignore your 1. You'd have a 2 secant squared. Derivative tangent secant squared, 2 carries along. Over your x derivative. Again, ignore your 2. Derivative secant tangent. Is this too fast?
No, I'm good.
Cancel your secant there. You wind up with twice secant over tangent. We want to plug in pi over 3, negative pi over 3. Now, if you're good enough to do it directly, great, or you could do it from sines and cosines. You could, I don't know if you find it easy to plug into sines and cosines. Twice, 1 over cosine over sine over cosine. You wind up basically with 2 over sine. You really only have to plug into 2 over sine with theta equal negative pi over 3. So you wind up with 2 over sine of negative pi over 3. Sine, I'm teaching trig right now. So negative pi over 3 is down this way, negative pi over 3, and your sine's your y coordinate. You'd be at negative root 3 over 2. So you'd be at 2 over negative root 3 over 2. Hope y'all know your unit circled. Haven't forgotten it. That'd be 2 times negative 2 over root 3. Looks like it'd be negative 4 over root 3. I bet the book rationalized that. Let's see, this is 10, 3, 15. Okay. So the book wrote the formula out as I got 2 over sine. The book got 2 cosecant. And then at negative pi over 3, okay, they've rationalized it. Negative 4 root 3 over 3. So if you go root 3 over root 3, there's your negative 4 root 3 over 3. Oops, I hope y'all, am I back? I went unstable there for a second. All right, we convinced about dy dx? Do you want to see the second derivative?
Let's keep going.
Okay. Second derivative says take d dt of my dy dx and divide it by dx dt, which we've already done. The dx dt, I did it in my head, didn't write it down, but the dx dt is secant theta tangent theta. That's right. Dx, well, they're using thetas instead of t's. D theta is secant theta tangent theta. So this piece is secant theta tangent theta. they're using theta in here instead of t. This is a generic formula in terms of t's. I hope the letter switch doesn't confuse you. It really should be d theta dy dx over dx d theta, which wound up being secant theta tan theta. Now the dy dx, if you remember, just showed that was our formula. Our dy dx worked out 2 over sine. The book used 2 cosecant. Maybe I'll use 2 cosecant. That was wound up being 2 cosecant theta. d theta, 2 cosecant theta over secant theta tan theta. It really is nothing but plug and chug, but I know that's easy for me to say since I've worked with it a lot longer than you have. Y'all remember your derivative cosecant? I think you'll find it's 2 negative cosecant cotangent. Apologize. Over secant tan theta. And remember, we want to plug in negative pi over 3. We're going to be here a while. Now, I did plugging in. I've already done that right here. Basically, yeah, that's your negative cosecant theta, or your cosecant theta here. That's what we plugged in right here. And see what we got. We worked it all out. So we've already done this piece. It's negative 4 root 3 over 3. This piece by itself is negative 4 root 3 over 3. So there's no point in reinventing the wheel because dy dx worked out a cosecant, and we've plugged in negative pi over 3 into our cosecant. Oh, wait a minute. I think I'm screwing up the 2's doing that because I have the 2 figured in. Yeah. Yeah, this gets, I had the 2 figured into that, didn't I? All right, so do you need to see this finished, or you all think you can plug negative pi over 3 into this? You wind up with negative 2 cosecant theta cotangent theta over a secant theta tan theta. Again at theta, negative pi over 3, which means you wind up with negative 2 cosecant of negative pi over 3, cotangent negative pi over 3. This is a project, not a problem. You all think you're, this is like a trig nightmare. You all think you're capable of figuring all that out and get to the book answer? Or anybody want to see me take the next 10 minutes and do it?
I think we can handle it on our own.
Okay. That's base. Okay. Just to finish up 10.3 here, the next little we're going to ignore equations of tangent line. There's a lot of Calc 1 in here they want to make you do, and we don't have time to mess with it. We're going to ignore equations of tangent lines. Again, up here, find equation, we're going to ignore that. Again, this section, find equation, we're going to ignore all that. This horizontal and vertical tangency, though, that comes up a lot, and actually that's pretty straightforward. It's a half problem. Let me show you what I mean. Horizontal, this is called horizontal and vertical tangency. It's basically a half problem. All right, the full problem is dy dx, and you're taking your y derivative dividing by your x derivative. This is the full problem, all the pieces. This has got all pieces. All right, I'll draw a quick curve and then do this. Okay, you see that this piece is horizontally tangent. Right there, right? horizontally, that means your slope is 0, which means your dy dx equals 0. Well, when you look at this, if your dy dx is 0, 0 equals dy dt over dx dt, which piece of this is going to be 0? It's got to be just this, must equal 0. Just your dy dt must equal 0. So for horizontal tangent, you set dy dt equals 0 and solve. You ignore dx dt. That's why I call it a half problem. You only care about the top being 0 for horizontally tangent. I don't know where that message came from. Can you get rid of it? Oh no, no, I shouldn't have messed with it. Blast. Can y'all still hear me?
Yeah, we can still hear you.
I don't know if I get back to the camera or not. Let me see if I can. Maybe I can real quick. Okay, can y'all see the camera?
Yes, sir.
Okay, so if you want to do vertical tangent like this is vertically tangent. Well, your run is 0. This means your dy dx is undefined. Your run is 0. In effect, you're dividing by, this means your dx dt equals 0. That's your run. This is your rise over your run. If you're horizontally tangent, your rise equals 0, which means your dy dt, you have no rise. It's all run. Here you have no, it's all rise, no run, 0 run. So for a vertical tangent, you set your dx dt equals 0 and solve. Ignore dy dt. Do you want to see an example how this works?
Yes, sir.
Okay. I guess we'll charge in. The first one's 31. 31. X equals cosine theta plus theta sine theta. Y equals sine theta minus theta cosine theta. They give you what it looks like. I won't take the time to draw it. But they want you to find all points of horizontal and vertical tangency, if any. Sometimes there aren't any. You can kind of see the horizontal tangent there, here, here, maybe down here. Vertically tangent, I don't know, hard to tell. It may not be any vertical tangent. Okay, so and by this, when they say find all points, they mean X, Y coordinates. All right, let's try horizontal tangent. I'm going to set, in this case, generically dy dt, but in this case, dy d theta, they're using theta instead of t, equals 0. All right, well, I kind of do it in my head, well, except that this is a product rule. All right, so your derivative of sine, I'll write it out real slow. d theta sine theta minus theta cosine theta. I want to set it equal to 0. So derivative of sine is a cosine minus big parentheses because this is product rule. First, derivative second, plus second, derivative first is 1, equals 0. Are we going too fast?
I'm okay to keep going.
Okay, cosine theta, distributing the minus sign through, I got a plus theta sine theta minus cosine equals 0. So negative times negative, that's a positive theta sine theta. And negative times cosine is a negative cosine. You see what happens? Your cosines, basically I got to solve theta sine theta equals 0. So we call this piece 1, piece 2. You're going to set them both to 0. Piece 1, theta equals 0. And piece 2, sine theta. I hope you know your trig circle. That means theta is 0, pi, and 2 pi. Now, we're not done. This repeats, so we have to do it once. We want to find our xy. So we've got to plug these in back up here and find our xy's. So I'll use theta equals 0. X would be cosine of 0. Add 0 sine of 0. 0, I'm sorry. 0, which would mean cosine 0. Your x is going to be 1. And your y is going to be sine of 0 minus 0 cosine of 0, which will be 0. Sine 0, 0, and 0 there makes 0. In other words, coordinate 1 and 0. See if you can, we can find y is 1. Let's see. Let's check that point just to see if I'm on the right track. The rest of it's more of a project than a problem. It was 10, 3, 31. They wanted, let's see, they're not doing X and Y coordinates. They're doing, well, I've got 1 in pi. Horizontal tangent 1 in negative pi. Well, here's 31. All right, I'm coming up with 1. All right, here's 1 and 2 pi. 1 and negative 2 pi. So I'm getting the 1. Now they're, instead of having angle 0, God, this gets confusing. All right. So 1 and 0, they're coming up with 1 and 2 pi, which is at the same spot. In the book, they have 1 and 2 pi. All right, so it's got to be that point right there. Okay, why it can't be 0? Oh, they're matching. Theta is 0. Theta is 2 pi. You're going to get the same thing. All right, I'm kind of baffled on why it isn't 0. Theta is 0 itself, 1, 0. They're using 1 and 2 pi. Okay, well, I'm sorry. I'm kind of, we're at full hour. Everybody's tired. And have I shown you enough? Or have I left you completely baffled? This is what you've got to do. You've got to plug, you're supposed to plug your theta values into, back into your x's. I thought they meant x and y coordinates, but they don't seem to be getting x and y coordinates. I think they mean x is 1 and theta. I'm leaving y'all all confused. Is this enough that y'all are dying to get away? Maybe we can pick up here next time.
That sounds good if we pick it up next time.
Okay, we didn't get to 10.4. 10.4 completely switches coordinate systems to what's called polar. But again, it's pretty much all trig. 10.4 is all trig. It's a lot of work on y'all this week, finishing these sections. And then if you want to look at the final exam review by next Monday or Tuesday. So anybody else want to say anything? Are you ready to call the meeting here?
I think we're good.
Okay, anybody? Yes. Anybody else want to say anything? All right, hearing nothing, then we'll call the meeting. And if you want to pick up with this next time, or we can pick up with 10.3 next time, depending on y'all's questions. But otherwise, we'll go ahead and call the meeting then. Hearing no objections. All right, we'll end the meeting.
Thank you.
Oh, thank you.
Okay.